Hello, thank you for coming to my seminar. I'm Santi Lee from CIMAN and AOML. And the collaborator and contributor for this work include the one from Fox from Geographic, and Molly from here, and Yan from here in CIMAN. The title of my talk is What Caused the Abrupt Increase in the Indian Ocean Heat Content during the 2000s. Yeah, so a little bit of motivation for this study. So what I'm showing you here is the global surface temperature that includes the surface temperature of the ocean and the land. Since the 1950s, and this is the black line is the observation. You can see this global warming pattern. But if you take a look at what happened during the since 2002 and onward, it has been quite flat. So this so-called recent global warming hiatus has been a subject of a very intense study in recent years. And then these people, Professor Lee and England et al., and also Neil et al., 2011, they come up with the hypothesis that this La Nina-like condition in the tropical Pacific is responsible for this global warming hiatus. So the idea is this, if you have a El Nino situation, the heat is released from the ocean to the atmosphere. In the opposite situation, the La Nina situation, heat is coming into the ocean. So that makes sense how it is possible because during the La Nina conditions, the temperature in the tropical Pacific will be colder, so that the long wave rate cooling will be reduced. That means more heating into the ocean. So these people, Professor and me, they performed very interesting experiments. So what they did was they performed this a couple model simulation. They put greenhouse gas in observed CO2 and aerosol, and they run their couple model. And then that's the result is this history run. And it's just increased as it should be. Then they performed the same experiment, but except that in the tropical Pacific, they left the couple model SSD toward observation. So they artificially putting this natural of the La Nina condition in the tropical Pacific. Then their result, this red line shows that it's flat. So they actually very nicely, Professor and Steve demonstrated that it is a La Nina-like condition in the tropical Pacific that is creating this global warming hiatus. And the other studies, such as McGregor et al., they suggest that the ocean is responsible for these La Nina-like conditions in the tropical Pacific. Other studies, such as Tokunaga and Moore et al., suggest that it's the Indian Ocean warming pattern in recent years that is creating this tropical La Nina-like condition in the tropical Pacific. And then Chen and Townsend was published some months ago, suggesting very different hypotheses. They say it's not tropical Pacific receiving more heat. It is highlands in the Atlantic. There, the heat is actually dumped into the deep ocean, and that's where this missing heat is going. That's what it is. So there are many different hypotheses, and then new papers coming out almost every issue of natural climate change and other journals. It's a very active area of research. So and then this NOAA et al. In 2012, they used the satellite data to show that the net radiation imbalance at the top of the atmosphere is continuing throughout this hiatus period, which means Earth is warming overall. And then, according to this new paper by Trenberg, which appeared in Journal Climate this year, they suggest that this about 90% of net radiation imbalance in the tropical in the top of the atmosphere was actually dumped into the ocean. Only the 10% was used to warm up the atmosphere. So, according to, consistent with this, all this suggestions, what I'm showing you here is the global ocean heat content in the upper 700 meters derived from the NOAA NODC World Ocean Atlas. You can see that global ocean is warming up even during this hiatus period. basin, we see something very interesting. First of all, this is Atlantic part, this is the Pacific, this is the Southern Ocean, and this is Indian Ocean. And I'll show you in the next slide how I divide these four oceans. The Atlantic Ocean here in this analysis includes the Mediterranean Sea, Labrador Sea, and the Iceland Sea, the Greenland Sea, Iceland Sea, and the Norwegian Sea. Very simple pronunciation. So they call it ENSO here. And then the Southern Ocean is just south of the 34 degrees south, everywhere. And then Pacific Ocean is all this, and Indian Ocean is this. And then Indian Ocean and Pacific Ocean come only through this Indonesian passage. So here is Pacific, and here is Pacific, and that's the Indian Ocean. That's how I define it here in this analysis. So let's go back. And then first thing we notice is that the Atlantic Ocean warmed up faster than other oceans. And then that we published a paper in 2011 with some hypotheses and all that. So that we really did that work. And then this is, but if you take a look at what happened in these 10 years, for instance, starting from 2002 or 2003, Atlantic warming has been almost flat or a little bit decreasing. And also Pacific is also flat or decreasing, and that is inconsistent with what all these people saying that all this heat, extra heat is dumped into the Pacific to warm up to the right condition. But this model, this data doesn't seem to support that idea. And unlike these two oceans, the Southern Ocean has increased a lot. And that's not surprising because it has been warming up all throughout since 1960. And then what is interesting in the Indian Ocean, which is the focus of the study, is that during this period, all entire period, it was quite flat for some reason, and there was a little bit of heat there, and then increased substantially during this period. And if you look at the slope, it's like a very slope is very steep. So this table is very important. So this what I'm showing you here is the rate of the ocean heat content changes. So you can think of it as a slope of the heat content changes. Average for this period, 71 to 2000, and another one, average for 2001 to 2010. So this the storage rate, so it's not heat, it's a slope during this period. It's about 3.1, the unit is here, okay? And what I'm showing you here in this parenthesis, I need to explain carefully. This value is based on an assumption that this warming here, global warming, the global ocean warming, the heat that comes to the ocean is evenly distributed. Then this is theoretical value. So, for instance, Atlantic Ocean is about 20% of the global ocean in terms of surface, in terms of surface area. So we need to have like 20% to come to theoretical value, just to give you an idea. And Indian Ocean is only 12%. The Pacific is about 40%, and then the Southern Ocean is like 30%. So this is an ideal situation. This is what we're supposed to get. So what is tracking here is the Atlantic Ocean. Here it warms up faster than any other ocean. Like I said, it was published in 2011. And the Indian Ocean is decreased a little bit, but this difference between the theoretical value and real value is very small anyway. So it's difficult to say that it's different in significance, that it's safe to say that it's kind of flat. And it's gone. It's very small. So the Pacific is about 1.1. That's what we expect. So the ocean is about the same. So let's take a look at what happened in 2001 to 2010. We have the heating rate is more because we have more greenhouse gases. Atlantic, 1.5, about what we expected. So, okay. And the Indian Ocean, we're supposed to get like a 0.9, but we have 2.3. That's a huge because the Ocean only 12% of the surface area, and the heating rate is very, very large. And then Pacific is very surprising because it's supposed to be at 2.8, but it's only 0.9. And then, like I showed you earlier, like if we shift this window to 2003 to 2012, for instance, this will actually become negative. And then here, subnutrient increase as well, but that's what we expected because subnutrient is huge.
So for the Atlantic, that wasn't decreasing, right, over the last decade? In the Atlantic, you showed on the previous slide that it was decreasing during the last decade.
Yes, that is true too. That is true too. But the value that I show you was like here. Yeah, the point if I move it a little bit, window here, that'll be negative almost black. Oh, by the way, I'm showing everything is upper 700 meter because data below 700 meters is not pretty good. So we have two questions. What caused the abrupt increase in the Indian Ocean content during the 2000s? And what caused why the Pacific Ocean econ did not increase much during the 2000s? Because, according to the old previous study, Pacific should receive a lot of heat.
You say if you consider the data below 700 is no good. I would say that there is not much there.
That's very difficult. Right? Yeah. So what this NODC website provides is that below 700 meter, 700 to 2,000 meter, up to 2,000 meter, they provide only from 2005. Before that, they don't think it's good. So I don't know. But only from 2005, where we have a fair number of overflows, and before that, they don't provide. All right, so let's go to to explore this two very interesting questions, we use surface force, ocean sea ice, ocean and sea ice model simulation. So this is a model. I'm going to spend next 3 minutes to talk about a lot about it. So if you're not interested, you can just close your eyes. Think about something else. I think it's boring to you, but it's very important. So this is I like this 20th century analysis because it covers the entire period, entire 20th century and more. And I like it also because it's only the synoptic surface pressure and surface data was assimilated into the model. So it's relatively more effective for long-term planning and search. If you use the NSAT analysis, for instance, it goes back to 1950s, but due to the changes in the observation network, you can introduce a lot of big jumps and changes in the analysis field. So I really like this one. Yeah. So I used it, and then we used that in the previous paper too. So the ocean model we use CESN1, and so in the previous study 2011 we used the CESN3. Now they changed to CESN4, and they changed the name to CESN. Now it's a community Earth system model instead of community climate system model, because they have biological geographic components as well. So this is still a 1 degree kind of resolution model, but the vertical resolution was increased from 25 levels to 36. So we have more vertical resolution, and they said that the NCAR said that they included this parameterization for the Denmark overflow. They said this is very big improvement to the thermal circulation. And also it's coupled to the CIS model. And another very important thing that is relevant to this study is that ocean response to southern hemisphere wind changes are really better with a high resolution model, because one of the big problems in the low resolution models like this is that it's too sensitive to the change in the westerlies in the Southern Ocean. But according to high resolution model, it's not that sensitive because eddy will compensate that the change in flow. So the change in circumpolar current and magma transport, those are the heat transport, radiant heat transport, that's really small. But they actually put some specially varying diffusion coefficients for the Jensen and McWilliams parameterization. So they claim that they improve it, and there's a paper about that. But it may not be perfect, but at least an improvement. So we have a speed-up simulation that reports the loading model for 400 years using the forcing field from 1948 to 1977. Right? And then afterwards, we run it for another extra 600 years. So after this, simulations, and we call it reference experiment because I'm going to compare that with the control simulation. In the control simulation, we have a 6-member ensemble simulation. So using the 20th century analysis for the surface forcing field for 1948, which is done to us for 65 years. Now, all the ensemble model, they are identical except the initial conditions are different. So initial condition taken from the reference experiment, year 401, year 501, so on and so forth. So we have a different initial condition. And what I'm going to show you next slide are the composite mean of the 6-member ensemble and the model spread. The model spread is, we need to think about it because that's kind of an ocean internal variability that we cannot really resolve in this surface force model simulation. Okay, so this is the model result. This is the global ocean heat content change per 700 meters, and the black line is observation, and the green line is the control simulation, and the yellow, this orange line is from the reference experiment. So two things we can notice. First, there's model treats in the reference experiment. So if the forcing is almost chronological, then there is no trace. So that's a good thing. Second, the control simulation reasonably reproduce the observed global ocean heat content increase in 1950s. And there are some differences here and there, all that, but overall, it was pretty reasonable. And then what I'm showing you here is this. This is the heat budget sum. And this is integrated all over the global ocean. So here, and then this green is the average for 1971 to 2000. So this, okay? For instance, this is storage rate, this is heating, warming rate, rate of heating, rate of warming, rate of ocean heat content change is about this, when we average this. For this period, 2001 to 2010, so that's what it is. And the first term is the storage term, so that's the rate of heat content changes. And this is the fraction term because we are looking at only the 700 meter, so the heat can be dumped into the deep ocean. And this is a net flux at the surface. So we can see that the major contributor to this warming is due to this. Yeah, this is the surface flux term. This is short wave radiation, long wave downward, long wave upward, latent heat flux, and central flux. So you can see that major contributor is the downward long wave radiation that is associated with the increased greenhouse gas, including moisture and CO2. So we see that greenhouse gas warming is accelerating compared to this period here. That makes sense because we have no greenhouse gases in the atmosphere. And then the major term that is damping this increasing is the long wave up because because of the temperature warming up, long wave cooling will be larger. So that's accelerating as well. Latent flux, I think it has to do with the increase in the wind stress all over the globe, especially in the Southern Ocean. That increased wind is responsible for this, and that intensity flux is positive, which means atmosphere is warming faster than the ocean. So it's heating, so atmosphere is warming the ocean through the density flux. Okay. So let's take a look at the Indian Ocean. So the same thing, but I'm showing you only the Indian Ocean. So the control simulation experiment captures the abrupt increase in the ocean heat content and data heat content during the 2000s. And then it also was able to produce this almost flat heat content increase. But it failed to produce this heat flare in this period, and probably had to do in the period 1997, probably. And for some reason, the model is not like that. But at least the model gets this part. So, and then when we take a look at the heat budget, that's very interesting because if you look at this period, 2001 to 2010, this period, surface warming is not that much. It's almost flat. And then, but it warms up a lot. Heat content is slow it. Why? Because of the horizontal convection. And some of the heat are coming from the interocean transport, for some reason the deep ocean, but it is really, really large. So it is means it's this horizontal convection for the Indian Ocean. It can come from either the Pacific Ocean or from the Southern Ocean that's connected to the two openings. So this is a very important one. Second one, this is the Pacific Ocean. So here is the model, observation, reference experience. The model was capture this kind of a downward trend here, which is very interesting. And then what is very interesting here is that surface heat flux over the Pacific Ocean has jumped up a lot, which is consistent with this, all these people saying the La Nina-like condition in the years, Pacific Ocean will do a lot of heating, and that makes sense, and it's really consistent. However, much of that was actually removed through the interocean transport. Only a small portion was used to warm it up, because we are looking at if we move it up our window a little bit here, it will be negative. So anyway, interocean transport is very important. So in the previous slide, we see that the Indian Ocean is getting some heat through the interocean exchange, and the Pacific Ocean is losing through interocean exchange, which suggests that there has to be increased specific to Indian Ocean heat transport through the Indonesian passages during this time. So let's take a look at this Indonesian throughflow a little bit. So this is the heat transport across the Indonesian passages from the model itself, and then this gray line shows the reference gradient. They all are complex means, and then you see that we don't see much big trend there, but however, this reference the country experience, and you see that there is some increase, especially this particularly this particular year, and it's 2006, 2007, and 2002, 3 years, there's a big jump there. And then when we take a look at this reference experiment, the heat transfer is about 0.94. It's all negative because it's going south. We're looking at the equator, we're going south. So negative means it's negatively. So increasing this rate, right? The direction. So according to the previous studies, based on observations and the model studies, they suggested like about 0.5 to 1.1 terawatt. So our model reference experiment falls around between ranges. And then for this period, 2000 to 2010, that heat transport increased to 1.11, which is 18% increase from the reference experiment. So the question is, what caused this increase, particularly in heat transport in 2000? And before we explore that question, let's take a look at some observation, limited, but we have some observation there. First of all, this is, before I show you, I'll just give you a quick explanation of this Indonesian passage. So from the Indonesian throughflow is very complicated, but mainly all this water is mainly coming from the Makassar Straight. So out of, say, 50 square miles, about 13 square miles are coming from there, according to NOAA 2008. And the rest, about 2 squares, are coming from the northeastern passages. And then eventually all this 15 squares goes actually to the Indian Ocean, through the Makassar Straight, or Black Strait, and the CIMAN passages. So what we show is that if you measure this, you can get kind of a big portion of this Indonesian surface. So that's what Arnold Gordon and his collaborator in Lamont did. So there has been three observational field programs, Arizo, Instant, and then there's another one. It's kind of continuation, but the funding source was changed from NSF to NOAA, so they have a different name now. But this is the Makassar start with loss. So negative. I don't have a legend here, but the strongest one is like 1 meter per second. So what we noticed is that compared to this limit period in 1998, the velocity maximum has much increased afterwards, although there has been some gap. 2004, 5, 6. So, and then another thing that is very interesting is that during this 2006, 2008, and 2009 has been a lot of increases. And also this core of this velocity maximum moved up. And because the temperature here is warmer than temperature here, so that means heat transport is more effective there. So that is kind of a consistent. But this one is I took it from the project website of the Lamont, operated by Dr. Gordon. But I don't think this is published results. Probably this is kind of like I don't know exactly what it is, but it's not published results. The published results I will show you was published in 2012. They show it only from 2004 to 2009 period. And the result is a little different, but there I show only up to 300 meters, but this one will go all the way to 800 meters. And then, by the way, the Makassar Straight, the maximum depth go all the way to maximum depth to 2,000 meters. But anyway, what is consistent in the previous slide is what this is published, so we should be able to one more. That the Makassar Straight throughflow increased substantially during 2 years, 2006 and 2008. And then our control simulation suggested that that was we had 2006 and 2008 was a large increase, and 2007 also. So it's a model result, and the observations are more or less somewhat consistent. So to understand, so let's go back to this original question: what caused the increase, particularly in heat transport during the 2000s? So this is the Indonesian throughflow is a very important part of the global overturning circulation, but unlike Atlantic overturning circulation, it is mainly wind-driven, not really some other driven. We know that the wind is very important. So we performed some experiments here, three sensitivity experiments. First experiment, sublimation experiment, is the same as the control experiment, except that wind is real time here, same as control simulation. But in the Indian Ocean, Pacific, and Atlantic Ocean, we get the pharmacology of wind. So wind doesn't change, but heat flux changes. Only wind doesn't change. There is no dynamic effect. Similarly, in the Pacific experiment, the wind is changing only in the Southern Ocean and the Pacific Ocean. In the Indian Ocean experiment, it's real-time wind only in the Indian Ocean and Southern Ocean. Climatology here and there. So otherwise, all the three experiments are identical to the control simulation. So this is the result, and it's very complicated, but I'm showing. But you can pay attention to this red one. That was Pacific Ocean experiment where we allow realistically only the Southern Ocean and the Pacific Ocean. And you can see that most of the heat increase in the experiment was reproduced in these experiments, suggesting that Pacific Ocean wind is very important. And then if you look at the heat budget term, you can see that this is red. Color is matching with that. So that you see that large increase in the large Indo-Ocean emergence into the Indian Ocean. And then what is interesting here is that if we allow realistic wind only in the Indian Ocean and the Southern Ocean, we have a little bit, not really a whole lot, but we put some portion of it, and then if you look at this inter-ocean transport is opposite there too. And if you look at the Southern Ocean experiment where we do not allow realistic wind in the Pacific or the Indian Ocean, then it's kind of like that. So it's very small there. Increase very small, and then increase very. But here is, yeah. There are more stories to than that, but that's what it is. And then let's take a look at what happens to the Pacific Ocean. What is interesting here is that only in this experiment, we get it going down. And you can see that similarly, you can see that heat loss to the Indo-Ocean exchange increase only here in this experiment. So again, it's showing that Pacific Ocean wind was responsible for it. And then Indian Ocean also a little bit. So Indian Ocean was also a little bit responsible for the result value. So let's take a look at the two-dimensional structure of the heat gain and heat loss. So again, here I'm showing you here is not the heat content; it's the heat flow within 2001-2010, which means there's a warming trend here within that 10-year period. Warming trend. So you can see that the Indian Ocean is warmed up, mostly positive, so it's warmed up everywhere, but especially it's warmed up around in the South Indian Ocean, around 10 degrees south to 25 degrees south. And then this is the heat flux, net heat flux during this time. So the warming in the Indian Ocean is mainly here in the equatorial part, and this is related to the recent warming in the Indian Ocean in the western part around here. It's warmed up everywhere. The heat of the temperature structure, which I'm showing you, is related to that. But the entire heat content is not here. It's maximized here. And what I'm showing you here in the green line is the objective heat flux conversion. This is due to the heat transport in the ocean. So you can see that heat increase is due to this ocean heat conversion. And I'd like you to pay attention to this part here. We have heat loss a little bit, increasing, and that is associated with this objective heat flux factor here. And you can see that, heat loss is very small there. And the red part, of course, that heat has to be increased because there we have laminar accumulation, we have a lot of heat coming in, so heat should increase there. So it is objective heat flux conversion that is responsible for this increase in heat content increase. And there are a lot of interesting things going on there. I have no idea what is causing it, and I'm not addressing it today. I'm not discussing that more today. So what I'm showing you here is the heat transport in the upper 7 millimeter. Everything is 7 millimeter. So you can see it. And then the color line here shows the tropic stream function, which shows the wind response of the ocean. So this is anomaly from 2001 to 2010. So this is the average anomaly. And then what I'm showing you here is the wind change. Wind changes between 2001 to 2010 minus the wind in the total wind in average with 2001 to 2010 from the control experiment minus that of the reference experiment. So you can think of it as wind changes through this period. So yeah, this is the average only over the specific domain total average. This is average only in the Indian Ocean. And this is average only in the Southern Ocean. So it's a different name that I'm showing you. So you can see that due to this wind stress curve change, increasing trade wind and wind stress curve changes, we see this anticyclone, anomalous anticyclone, that increase the North current in the North Pacific, going that way, and also due to the increase in trade winds. So that increase, so that creates this anomalous stress curl that also increases the south equatorial current in the Indian Ocean. So that is converging to here. This is diluting from here, and that is the two wind-driven anomalies are connected through the Indonesian throughflow. So that's why I think we see exactly equal factors here, equal convergence here. So this is a summary of my talk. So there has been massive heat gain occurred in the Indian Ocean during the 2000s. And that accounts for about 30% of the global ocean heat gain during that period, and its contribution is largest of the four oceans. On the contrary, despite the much increased heat uptake in the Pacific due to the La Nina-like condition in the tropical Pacific, the heat gain in the Pacific during the 2000s are very small, and its contribution is the smallest of the four oceans. Of course, like I showed you, heat flux into the ocean is very large during this period, but actual heat content increase is very small, or very small. And then, so we use the surface force ocean CX model simulation to show that there is a large increase in the Pacific to Indian Ocean heat transport through the Indonesian Passage during this period, and then it's also more or less or somewhat consistent with the direct measurement of the Indonesian throughflow for this transport. And then we further found the model further suggests that the increased Pacific to Indian Ocean heat transport is directly linked to the increased trade wind in the Pacific and also in Indian Ocean, associated with the strengthening of the north equatorial currents in the Pacific and the south equatorial currents in the Pacific, in the Indian Ocean. And these anomalous wind-driven ocean dynamic features in the Pacific Indian Ocean are connected through the Indonesian throughflow. And this is it. And then I have other slides further discuss about. So the question here is of why the trade wind in the North Pacific and South Indian Ocean increased during this period. So that's really interesting questions. I have some other slides. So I have 2-3 other slides to discuss about it. Maybe I'll go on. It's just expensive 7 minutes. I'll just use another 5 minutes. So let's just think about the changes in wind changes in a global warming and ENSO context, because we want to know why this thing increased during this time. So let's take a look at the global warming first. In a warming climate, the atmosphere can hold more water vapor, and therefore the tropical, because it's warm air can have more moisture in it. And therefore, the tropical rainfall and the heat convection become less effective. I don't know if Tony is here. Tony is here? Yeah. Tony's not here, but he will be the good person to ask this thing. So I don't know very much about it. This is just my summary of the understanding of this. Well, so anyway, this means that the rising motion of the maritime continent should be reduced as well, and that leads to reduced water circulation. That's what Helen Soden suggested, and it's shown in this is Becky and Soden, and this is the pressure velocity at bottom. This is negative here. The pressure is a rising motion, but it's negative because the pressure is this way. So we have a rising motion here. In the global warming situation, we have this rising motion is reduced because water circulation is reduced. That means there's an anomalous subsidence there in the global warming situation. Now, let's think about it for ENSO situation. Here, this is normal condition for the water circulation. We have a major convection center here. And during the El Nino, this convection center shifts to the east, so that there is an anomalous subsidence over there. And then the La Nina condition is opposite. The convection center here intensifies, so we have intensified water circulation. But in a global warming situation, which is similar to the ENSO condition here for this context, you can see that trade wind here direction. So because both, so that's what I just said, and the reason is because the local circulation strengthening and weakening is all related to this infrared greenhouse gas. So what it means is that so let's see. So in an earlier situation, for instance, the wind, the trade wind is decreased so that there has to be the inhalation throughflow has to decrease. However, there is if the wind is anomalous wind is going that way, that will try to increase it. So they compensate each other. The same thing. So we have you can think of it in terms of pressure in the La Nina and Nina situation, with specific pressure. What happened in the Indian Ocean, into the Indonesian Gulf War, you can think about it. That pressure changes as the pressure increase together and decrease together, so they compensate. So there's no big, huge Indonesian throw flow there. So it's so negative correlation. So Indonesian throw flow should remain relatively small. So the question is, now in the Pacific, the trade wind was increased because of land jumping, and that makes sense. But in the South Indian Ocean, the trade wind was increased. So that makes sense why the Indonesian throw flow was increased, because we had high pressure in the Western Pacific, we have low pressure in the Eastern tropical Indian Ocean. So there's huge Indonesian throw flow, which I haven't really taken a look at the model results yet, but that seems to be what should be happening. So why this is the case? And then one hypothesis is that that the Western Indian Ocean has been the sea surface temperature has been increasing consistently throughout this 20th century, and perhaps that's the reason, because the Indian Ocean western part is increasing. As it's increasing, the trade wind has increased, diverge and converge to that region where we have anomalous more precipitation there. Maybe that's the reason. Who knows? And then those kind of we can come up with many different hypotheses, but to test that, we need to use a couple more simulations to test that hypothesis. So one last thing that I want to mention is that there are many other products other than World Ocean Atlas. For instance, Ishi data, which was used in Chinatown in 2014. This data in general, all the increase and decrease in different oceans, it's more or less consistent with World Ocean Atlas, but this one, Ocean Reanalysis 4. This is basically a data accumulation product operated by the ECMWF. But they show this different results. Indian Ocean sea content does increase, but it's not as steep as what other the World Ocean Atlas suggests. And in their simulation, in their work, Pacific Ocean sea content increases. So there is some discrepancy between these three things. But I have to say, this is model, that's data, this is data. I think that's it. And then I have other slide about what happened at Atlantic Ocean and Southern Ocean, but I think wait. Hang on.
So the second feedback you use in NOAA is reflect on 2020
It is. So what happened here is that the radiation components, short wave, long wave down, short wave down and up, that's prescribed from the 20th century analysis. But the long wave radiation, upward radiation cooling is related to SST, more SST. And then the wind is prescribed, but letting it flow through the air temperature changes. Every air temperature is fixed, but SST changes. So it's a little bit changes. One more thing that I have to add is that this 20th century analysis has some bias. So I used observation to minimize that bias in all the atmospheric pressure.
Yeah, because it's a prescribed and then the heat content changes, and then you use so the temperature flat to the ocean.
That is true.
Right?
That is true. I mean, if we integrate all the global ocean, there's no way to transport it in and out, so it's all about heat.
I think the agreement given the sequences for the reason in the moment, if the heat factor is less, then you do that increase that because it's really
It is. Yeah. But the heat content in the model and observation is pretty much the same, which means for some reason this is doing the right thing. But I have to say that this is 20th century analysis is not observation. It's also atmospheric analysis. They decrease the SSD and surface pressure, but they increase the greenhouse gas, CO2 according to the observation. So that's based on models and quantification.
You have the heat fluxes from the going to the Indonesian throughflow. That's associated with the net volume flux.
I think so.
Right. So I was wondering whether the change in heat flux is associated with a change in the volume flux or a change in the temperature structure.
That's what I'm going to do next.
Let's see.
Yeah. I haven't done it.
Okay.
Yeah, that's what I'm going to do.
Okay. And my other
Probably
question
today.
was about the vertical structure of the change in the inclination of the heat content change.
Right.
So I wondered if you could say anything about that as to the top 700 meters.
In the model.
Well, either or both.
Yeah. Temperature.
Yeah, so I'm kind of curious as to why the southern parts of Mozambique and the variability that we see in the gyre and the South Indian Ocean isn't playing more of a part. And so I wondered if the depth structure shows that up or whether it was more surface intense.
Oh, that's a good question. That's a really good question. That's something I was thinking about it too. So I don't think I will directly answer to your question, but I have something related to that, the issue that I was thinking about. So I was thinking about why the Indian Ocean, the heat content was not increased from 71 to 2000. And then I think that may have to do, I'm not showing it here, but that may have to do with the fact that surface is getting heat, but due to this change in the release, probably I should read the next one. Due to the change in the lunar strength and the depth of the steepening and shallowing of the thermal line, so probably there's something to do with it because model from the future suggests that heating during that period was dumped into the deep ocean, and that probably has to do with the wind change here, that intensified the structure of the gyre, and then that means the steepening of it. So some of the heat was probably went out there due to the dynamic thing, not due to some dynamic thing. And then I have a look at it. That's one other thing that I'm trying to look at, the vertical structure of it. I like to look at the vertical structure here, vertical structure here, vertical structure here. All right. Thank you very much. Thank you very much.
Yeah.